Sound check. Sound check.
Good morning, everyone. Welcome to the third day of Cyseni conference. And now I want to introduce the first speaker today, and it is Ruan Merbekova from Iceland. Please.
Thank you for the introduction. So, unfortunately, my colleague Gudmundur cannot present because he's sick, but I'll try my best to present, and it's a great honor to be here.
A second.
The topic of the presentation is CO2-free aluminum for energy storage. Okay. So, how much energy can we get from the aluminum? The thing is with aluminum loves oxygen. That's why it oxidizes very easily. And it's exothermic reaction which creates energy. So, that's why, for instance, in industry, you require lots of electricity, energy to produce aluminum. This will be reverse reaction. And this is a laser. Yeah. So if we go to the reverse reaction, that's why industry requires a lot of energy. So if we're gonna look at the, for instance, energy content of the different fuels per mass, for instance, here is shown per mass in this figure. You can see that, for instance, hydrogen is very attractive fuel, but this is true for gravimetric energy. But in the long storage energy density in volumetric specifics is more important than the gravimetric ones. So, for instance, if we're going to plot it in different way, in this diagram, in the per volume, then you can see that aluminum becomes the most with the highest values. So aluminum can be a good material for energy storage. Aluminum powder should be can be used for the combustion, but the thing is with that is that you have to have a low particle size, and the particle size should be less than 25 micrometers and preferably less than 10 micrometers. And this can be like combusted very easily just as a coal. You combust the coal. This has been investigated by many actually researchers. But the thing is, for instance, with the ingots, okay? For instance, here, there's a picture of the ingots. This is very for instance, a safe material, because if you're gonna try to burn it, it has a surface layer, a strong surface layer, this aluminum oxide, which prevents it burning further. But in case of particle, it becomes like a chain reactions, which can continue. And that's why it's easier to burn the aluminum with a less particle size. So one of the examples where aluminum is combusted is in rocket propellants. So what you do, you use as a fuel a mixture of aluminum powders, ammonium perchlorate, and a binder. So you use aluminum as a main fuel. And ammonium perchlorate, and here divided to perchlorate is an oxidizer, and ammonia is a source of energy. And the poly between acrylonic gel is a binder. So this is a solid fuel, which is used as a fuel for these rocket propellants. When this fuel is actually used initial to start the propellant, further, the rocket uses liquid oxygen, hydrogen. There are safety issues with the fine aluminum powder. So, because it can, as we talked, it can explode. So that's why it's preferably that you have to have a particle size more than 420 microns. according to the aluminum association. And for safe handling, it should be granules more than 420 micrometers. But if you have a spherical granules, it should be you can handle around from 100 to 200 micrometers. So here is a diagram. What is interesting is that if you only have aluminum granules, it has a higher energy content than compared to the diesel fuel. So it's not only aluminum can be used as a metal fuel, as you know, there can be different other metals, for instance, iron and silicon and magnesium. And there is a quote which says that metals, and specifically metal powders, are promising a largely overlooked zero carbon recyclable fuel option. Metals are the most promising zero carbon fuel choice. But yet, like, just like that, not so much overlooked. Yeah. So the thing is, with the disadvantage of these metals actually is that it's very energy intensive to produce them, and these metals are not produced without CO2. So, for instance, if we take aluminum production as an example, so for instance, it's, as I said, like it's very energy intensive. So your CO2 emissions are primarily related how you produce your electricity. For instance, if you use coal, you can end up with very high emissions. And you can see here, it should be here, Norway and Iceland, which we use, where we use actually renewable energy to produce. We use renewable energy to produce electricity. That's why the emissions are very low compared to other countries. So, and mainly the emissions in Iceland and in Norway is due to the process itself. And so let's study how the aluminum production process works. Why do you get these CO2 emissions? And the process is like has a high temperature. It's about 960 degrees. And the reaction is like where you use raw materials, alumina, carbon electrodes to produce aluminum and CO2 emissions. So as I mentioned, this is very energy intensive, and this is electrochemical reaction. Therefore, you need 14 kilowatt hour electricity per ton of aluminum to produce. And so carbon nanos emit about 1.5 tons CO2 per ton aluminum according to this reaction. And alumina results also in CO2 emissions because producing alumina from bauxite is also connected to CO2 emissions. So aluminum electrolysis plants need a large space, mainly because of the horizontal electrodes. So for instance, it can be like usually it's so the space is so large that usually in smelters you have electric vehicles or vehicles that to move around the place. So here are the smelters in Iceland. So we have smelters from Rio Tinto called Isal, which requires a lot of current, 170 kiloamps, and Nordirol from Central Aluminium with 230 kiloamps, and Fjordal, which is from Alcoa, requiring 360 kiloamps. So you can see how much current you need to produce this aluminum. And as you can see in the pictures, so this is like requires a large space, takes a lot of land. So this is the illustration of the aluminum cell, and the same is with aluminum cell. As I mentioned, the operating temperature is high, 960 degrees, and also the alumina is very stable, as we saw. That's why you actually like need very corrosive environment to dissolve this alumina, which is cryolite, and it's so corrosive that to handle this cryolite, you actually need to freeze the cryolite itself to contain the electrolyte. So that's why most of the energy goes out through the walls. And as you can see here, the electrodes are located horizontally. This is our anodes, carbon anodes. And here's our cathode is a metal, and which takes up lots of space. So carbon anodes are consumed during the process, as you said, according to the reaction, and therefore you have to replace them when they get consumed. For instance, you can see here how the new anode looks with the carbon anodes, and you can see here it's being consumed. It's like a thinner portion left, and they remove it and replace it after 30 days. So this is a general, like how much you need to use electric energy. So it's usually the average is from 13 to 15 kilowatt hour. The best ones operate at 12 kilowatt hours. Actually, there are smelters which has that target. And there is a lot of energy comes also from burning the anodes, which is from 3 to 4 kilowatt hours per kilo. So the total energy consumption is can be from 17 to 19 kilowatt hours. If we compare to our previous reaction, where the combustion of aluminum produces 8.33 kilowatt hour, this is a large amount of difference. So this is not very efficient process. So the subject in Iceland has been like trying to produce vertical electrodes, inert anodes, which is the process of production of aluminum without CO2 emissions. And it's not only in Iceland, we have also other competitors in the world. It's actually only 3. One is in Rusal in Russia, and one is in Canada, LSIS, which is supported by giants such as Alcoa and Rio Tinto and Apple. And we in Iceland, tiny country with 360,000 population. So, but our technology has been very promising, and now we're going to be scaling up in Germany with a big company called Trimet. So this here, let me explain how this process works. So we need also raw material, which is alumina, and the reaction here you can see alumina dissolving into aluminum and oxygen. So you don't produce any CO2 emissions here. And you produce oxygen at the anodes, and you produce aluminum at the cathode. As a cathode, we actually use, I'll explain later. I think we have the slides. And yeah, let me show you another slides where I will talk about. Wait. Sorry, these slides have been prepared by my colleague, and actually last night I figured out I have to present this. Okay, I wanted to show. Yeah, here. I wanted to show you this is much better. So this is the cathodes, and this is the anode, and cathodes are wetted by aluminum, and they will be like dropping the aluminum into the bottom. And here our anode, which is gonna be a mixture of ferronickel copper alloy, and the main idea with these inert anodes, they should not contaminate our aluminum, because if you produce aluminum with impurities, then nobody's gonna buy it, so it's gonna be not useful. And the thing is with this the cathode, it's a titanium diboride, which is actually very strong material, ceramic material, and it's actually the second strongest ceramic material at 3,000 degrees. For instance, the fun fact. Yeah. Yeah. So the main challenge we have been maybe facing that it's we would like to have it like as I showed before. Do you remember in conventional cell you need the cryolite itself and frozen ledge outside to contain everything. But what we want here, we want no side ledge, no frozen ledge, because we don't want to lose any energy. And also this also gives us lots of flexibility in regard to like being the process flexible and adjust to like for instance renewable energies, because as you know renewable energies are not continuous. It can be like high demand sometimes when the sun is shining and wind is blowing, but there is yeah, and then when there is no wind or sun, you can be having less energy. So without these side ledges, we can actually like contain everything without freezing anything. Yeah, because in electrolysis, once you freeze in aluminum smelters, you can lose the process. For instance, there was a case where the smelter was lost just because of the power shutdown for 5-6 hours. And yeah, this is the status of this technology. So we have been demonstrating in lab scale for 50 amps, and we will be scaling up to 600 first, and then 2,400 amps and 10,000 kiloamps. So as I mentioned, we are in a cooperation with Trimet Aluminium and other European partners. Here you can see. So we have here Arctos Aluminium, our main partner in this project, and then we have Ricoh University, Trimet, Lancy, Access, Aachen University, University of Charlotte, Hana. Yeah, so back to aluminum as a storage material. So you can also oxidize aluminum in water conditions. As you can see here, aluminum reacting with water, producing aluminum hydroxide and hydrogen. So your byproduct will be hydrogen, which is also an exothermic reaction. And this hydrogen can be used to produce electricity and heat in PM fuel cells. For instance, it's an example of a project, Alice rocket propellant, and where here is Al stands for aluminium, and ice is like an ice frozen. So this frozen mixture of non-aluminum powder and water is used in this rocket as a rocket propellant, where the ignition starts with this reaction. Aluminum reacting with water and producing alumina and hydrogen. So we have one of our projects, also actually Alice Y, and this is Alice Y stands for the Aluminium Circular Economy from Waste through Hydrogen Energy to Alumina, and this grant is supported by EEA. And so we here investigate if we can, if the waste aluminum can produce hydrogen. So for instance, here, according to this reaction, aluminum reacting with water, as I mentioned before, producing aluminum hydroxide and the hydrogen. And our role is here is like investigating this byproduct, where we can use it. For instance, can we have good properties that it can be converted back to alumina and fed back to the smelters, thus it will be circular economy. Or maybe we can investigate other things because, because of the different properties. Yeah, so we have here different partners. You can see Lithuanian Energy Institute and the University of Iceland, and we also have Institute of Solid State Physics, University of Latvia. So I'm also gonna introduce another project, which is connected to similar example, where you oxidize aluminum in water and produce hydrogen. and it can be used as energy storage. So this is actually a quite new project. It started in July 2022. So this is co-founded by European Union Horizon Europe program and Swiss State Secretariat for Education, Research and Innovation. So what we do here, we develop solutions for storing large amount of electricity, and the storage should be very cost effective. So it has several goals. It's a seasonal storage also, and of course also closing the cycle where we will be taking our raw materials, producing something, and taking back in. And this technology should be based on the renewable electricity without any emissions, and it should be. And the process where you use the power to aluminum storage charging should be also emission-free aluminum to energy. And we also will do the economic analysis of the better economic analysis for the environment, how it impacts our environment as well. So the concept is that we like to store the energy for a longer time, because the thing is with current process is that we have a lot of solutions actually for the short-term storage. But when you have a problem, for instance, like let's say in Europe we had during winter time crazy amount of demand for the energy. Then for instance nowadays you don't need when the weather is very good. So what you could do is, like for instance, we could produce aluminum in Iceland where we have renewable energy, and this aluminum produced with renewable energy can be transported during winter time to Switzerland or other European countries, and there can be produced heat and hydrogen or electricity. So with this technology, what we promise is an attractive cost and acceptable environmental impact. So, like I mentioned, you use in this case aluminum as a fuel. So your fuel will be aluminum, and as we saw before the figures, you can see that energy density, the storage energy density is over 15 megawatt-hour per cubic meter, which is unmatched energy density to anything else. So you can have something very attractive solutions. So let me explain the process. So the process is that you take the renewable energy and you use this aluminum oxide to produce aluminum. And as I mentioned, during winter time, you would bring it the right place at the right time, and you would the discharging will be where you use this aluminum in a water reaction and producing hydrogen and the heat. And the thing is, we will be investigating two processes. One is like with cold water, and another one is with hotter temperatures. So it's going to be higher temperatures where you will use a steam. And the byproduct is also going to be alumina that can be fed back to the system. So, so we have 9 partners from 7 European countries. So you can see here from partners from Slovenia, Norway, Netherlands, Czech Republic, Germany, and Switzerland. This is a quite new, as I mentioned, quite new project. So we are going to be hiring lots of master students, PhD students, So if you have interest, please do not be shy. And I can share my business card later. And also we have, no, he didn't put the, we had also our another like social media page, but I think he didn't put it. So, okay. So ISTEC, our company, is a main coordinator and in this project. And so we have also advisory board in this, and we have for system analysis and flexibility and opportunities. It's also University doing it. And then for power to aluminum, we will be investigating because this is a process where you use energy to produce aluminum. And as I mentioned, in Europe, we are the ones who are developing how to produce green aluminum. So this part of the project is us. Yeah, and then we have validation. Yeah, is a closed material cycle, which will be SINTEF, our Norway partners. And we'll be doing like at the end life cycle assessment. And of course the dissemination and other things. Here he put it, sorry. So here's our details, so you can take a picture of it if you want, and you can follow us on Instagram, on LinkedIn, or other different social media. We also have an introduction video in this webpage. Yeah, thank you for your attention, and this has been a pleasure.
I want to ask if anyone has questions.
When does the aluminum get converted into powder? Does that happen right before it's converted into energy?
Into the powder. Yeah, it's the same as I showed, there was a reaction. You can see that aluminum reacting with water. And then actually, like for instance, aluminum has actually like a layer which is it's like very fake, and that's why we see it everywhere, you know, and, because it has this thin layer of this aluminum oxide, and we need to get rid of it. So there are actually different things that we get rid of it. So for instance, our colleagues here in the let's say, as they use last one, bombard is there, or you can actually get to the for instance, certain side or other solutions to remove this layer, and then this aluminum reacts, and then afterwards we produce hydrogen, and the byproduct is aluminum dioxide, or it can be aluminum dioxide, depending on the temperature of the reaction.
So will the reaction be a shrinking core reaction, or will they need unit operations to make the aluminum blocks into smaller particles?
No, so what we do, we can actually like treat as a sediment, or we can actually add an acid, and also solidify it. So maybe my anything if they mostly work with that, because the question was, she was asking, how do you like get this aluminum product?
I think the answer is yes. There will be needed the shredding. There is a previous mistake. And if the aluminum is not already particularly, it will have to be.
But usually, but usually.
I don't know if you're an expert on that, but if you are, please, we need you in the team. I mean, you're not, but you're right. The size is important thing.
Yeah.
And then the final process of the plate should be able to.
Or will that research come later?
Well, we are beginning to think of it, right? So there's many people in the team here.
Yeah.
We have been talking to it and getting ideas. It's tricky because if you ball mill, you need to keep the oxygen out and things like that. It can explode. But yes. I have a question.
Like collected and usually I haven't measured with the particle size, but it's usually like a solid powder.
I have a question. So the middle topic about the inert anode,
Mhm.
it's, as many of you may know, it's been decades, I think it's like 4 decades that we've been working on this. And thinking
Yes,
about
yes,
this.
yes.
And we are lucky to have somebody who's at the forefront of one of the companies that's doing it.
Mhm.
So could you tell us a little bit, just your own opinion about how far are we away? If you have to guess, no, it's hard to do. What's the closest and what's the road there that we could actually, and of course, the thing is to make aluminum without CO2 emissions, that's the dream, but we are not yet.
Yeah, this actually, yeah, this is true. It has been like many decades now being investigated, and many companies have been promising reduction of green aluminum without CO2 emissions. But I think we are now closer because there is like not that time, not like so many funds probably were made. Because I remember being a student, I really wanted to study this topic, but I didn't have get the chance to do it because this was not funded simply, for instance. And I was studying in Norway, and which is the like core center for the aluminum if you want to study something. And but nowadays, like we get a lot of funding, and the team is much larger, and there are like other competitors working at it simultaneously, and more investigation. So I think we are much closer now.
I think there's a good chance that this
Mhm.
will become commercial in at 5 years or 10 or 15.
Yeah.
Can you make a guess? I actually.
I would think 5 years, yeah. Yeah, that close.
No, that's,
Because the process is already like proven, it works, and but the thing is, we need to scale up, and I think a lot of challenges are gonna come with this.
there are a lot, you have pilot cell and
Yes.
you yourself have pushed the button and seen it work. I mean, yeah,
Oh, no,
That's what I
no,
suspect.
no,
Oh.
we're gonna start doing that.
Oh,
It's,
okay.
Yeah, it's gonna be with a cleanup company, so we are already building.
yeah, but you are
facilities.
doing,
At the, our
You're
lab, it's a
demonstrating.
laboratory scale,
Fantastic.
and it's much smaller.
well, but it's working.
Yeah, of course.
Yes,
But the process works, and we have the concept working, and it's proven. And we are doing, we will be actually doing some of the scaling ups at our laboratory, at our place. But the large ones, of course, we will be having at the smelters.
Yeah, as I understand, you displayed everything. You made aluminum, the aluminum quality is good, the energy efficiency
Yes.
is good.
We actually also like optimized our, for instance, electrolyte composition, because this process uses much lower compared to conventional. It's around 800 degrees, and you needed to like optimize which one is like not so corrosive, so you don't, because our anodes are metallic, so it's alloy, so it's easily can be like contaminating your product, but you have to kind of find and optimize your electrolyte, for instance, so you don't kind of attack like very badly your electrodes. And, so for instance, that one, and the temperature, what temperature is most suitable, and also the composition of the electrodes itself. Any more questions?
What happened to the offer?
I was hoping you don't have. Okay, the rocket, which rocket?
The one you showed,
The Alice rocket.
the one
yeah.
with the frozen,
Mhm.
the frozen field that was slowly defrosting.
Did it blow up?
Huh?
Did it blow up?
I'm not sure, This was just an example. Where
Oh, you don't know.
No.
I thought you
No,
didn't
no.
make it exploded.
This is the flight from Goodman direction.
Yes, I understand.
I understand.
Thought because you said, I hope you don't ask, it means it exploded. But it's still defrosting.
I do have a question about the titanium board. Who makes that and how complicated is the process to make that?
Yeah, it's our partners, mainly fancy swinging. Yeah, I'm not sure about the process, how they do it, so.
It's the heart of the secret, actually, I would say. probably for them.
Better not answer.
I don't know, I mean, yeah, be a lawyer.
Mhm. But it's very important actually, like there are actually like have been different, because titanium diborite is quite expensive also. There have been like lots of like thinking how to do it, or replace with others, or like even like do like titanium dipyrite coating on top of the carbon. So different ways I can like investigate it.
Do you know it's complicated to make it? If you want, then don't.
Okay.
Yeah.
I'm not sure. We don't do that part because our partners don't do that. So I'm not sure. I can give you the contacts. You can ask them.
Okay.
Mhm. Yeah, maybe you can like it.
No.
Yeah. Any more questions? Yeah. As I mentioned, we will be looking for more, master or PhD students. So yeah, if you're interested working with this technology, please, not be shy. You can talk to me, also ask more questions, maybe at the break.
Thank you. I want to give you some little thing. So as it's okay.
Okay,
Thank you very much.
Okay. I'll deliver it to Gudmundur.
You can share.
Okay.
So moving on, I'm gonna introduce to you second speaker. It's Professor Runar Untorsson from University of Iceland. Thank you.
Thank you. Good morning. Yes, my name is Runar Untorsson, professor at the University of Iceland. The topic of my talk is aluminum ion batteries. That's the journey I am on, and if I hope I use my time efficiently. At the end of this talk, you will be convinced, as I am, that this is a good journey to go. But first, who am I? Well, it's very, very difficult to define yourself, but it tends that when we go back, we always go back to our PhD. We spent so many years on it. So I did my PhD on acoustic emissions, which is a thing that it's basically pressure waves that are emitted in solid materials when the material changes. So pressure waves, and you can pick them up. So this happens in metals, ceramics, concrete, wood, plastics, ice even. You know this from, for example, if you put ice in whiskey, if you drink whiskey, you hear like, and you hear this is changing. But we normally don't listen to those frequencies. We listen to the frequencies about 25 kilohertz to 2 megahertz, mainly because it's a sensitive technology and you want to be above noise levels. So if you're high up, there's no noise. And it's a very sensitive method. Yes, I list this, but it has been used to, for example, listen to bone grow. You can't do that. It's also used in medicine, for example, when you have screws that you want to put in bones, then you can find out when you're just about to the maximum torque. You will hear some noises and okay, stop here. So the sensors, just a little bit introduction to this. So you have acoustic emission, some flow in the material, pressure waves are emitted, they randomly go throughout the material, bounce off the surface, but they will sometimes be picked up by the sensor. And the sensor is a resonance sensor. So it's very sensitive on resonance frequency, picks up this signal, amplifies it, and you get mostly spikes. And you cannot relate this exactly to the flow, but this is like a thermometer. You know something is happening, and there's a lot of processing trying to figure out what's happening. This is what I did with carbon fiber prosthetic feet. So I used to have this status. I break legs for a living. I don't know how many legs I broke, but you have to do a lot of sampling. So this is me, and I've been doing all kinds of stuff like this, moving up to audible acoustics, so virtual acoustics, calculations of acoustics in a room like this, tactile wearables using vibrations to deliver messages on the body for blind people, for people hard of hearing, and many, many other projects like this, gasification with my colleague here, Christian. But electricity, what can you do without it? Turned out when I was preparing, the power went out in Iceland, at least in my neighborhood. So one of the transformers broke. Took them 1.5 hours to fix it. And what can you do? I couldn't have myself a coffee. I couldn't even cook. I could not watch TV. Wi-Fi was out. I couldn't even clean my car with the pressure washer. It's electric. So you do something else. But with climate change, it's expected that there will be more extremes in weather. We will probably expect more blackouts, not only because of damages, but just disturbances. We're very sensitive to this. And as our electrical grids and all the electric stuff is becoming more complicated, of course, we can expect more failures. So how can we deal with this? One is to store energy, and so we can store energy in many ways, but one is using batteries, and that's my topic. We can use them as an uninterrupted power supplies, basically backup power. We know this from computer systems. We can use it to fill up gaps left by the renewables. So they're all variables, so you can have wind blowing and not blowing, you can have sun, and so this is not a steady source. So it's good to have battery to catch it. We can collect and prevent waste of excess energy. Sometimes we produce more than we need. It's good to then collect it and use it later. And as we grow up and have more advanced systems, we can then start to play the market. We can buy off peak and sell at peak, or even use it at peak, just to save money. And then there's the lower demand charges. I don't know if you, I mean, many companies, a lot of the industry is paying special price for high load. So it's an average energy used for 15 minutes in a month. So they split the month into 15 minutes, and the highest usage in one 15-minute interval controls the pricing of that part of their electrical bill. And just one high 15 minutes, and you have about 3,000 intervals in 1 month. If you have one really high, that will determine this part of your electrical bill. So you can use batteries to cut that down. So what type of batteries can we use? We can use new batteries. Then we just have the same battery, and we just make the battery storage system from new batteries. We can have second life batteries. Second life batteries are batteries coming from cars. Normally, batteries from cars are removed from service when they're down to 80% of their initial capacity. That there's a lot of life left, but it's not good enough for cars. So then we move them into some renewable energy storage, for example. We can also just use electric vehicles when they're plugged in. Can use them for storing and using. But there's a problem with that. the owner of the car probably wants to have electricity when he wants to drive, and they're not so reliable. I mean, you never know if they're there or not. So we can use them, yes, most preferably during night, but we can't really rely on them. So battery energy storage systems, they can be sized to your needs. You can have them, they're modular normally, so you can have just one unit, and if you need more, you just stack them up. If you need more than one cabinet, you can have many cabinets. You can stack them up and arrange them just to suit your needs. Even put them into containers and then connect all the containers together. So there's nothing really stopping you except maybe space and money. So who can use this? The end users, they can be from family houses. It can be residential houses with many apartments, hospitals. I mean, class 96 hospitals require 96 hours of backup power energy. And then you have class 110, that means 110 hours of backup energy. Normally today, diesel, with the CO2 and all those emissions. The TSO, the transmission system operators, that's the network operators, they are required to maintain stability of the system. One of them, we normally don't think about frequency regulation. We know this, for example, if you are in a hotel somewhere and you're in a shower and suddenly the water pressure drops down. This is very similar to frequency regulations. When you put a load on the system, the generators go a little bit slower, so the frequency goes down. Then you need a little bit backup power to push them up again. And they have a very tight limit. For example, in Europe, 50 hertz plus minus 0.2 hertz. So they are operating in a very narrow space. But this can help the system operators. It can also utilities or the small grids. It's those who are DSOs, so district operators. This can help them delay upgrading. When you have battery, you don't have to put in new lines or stuff like that, or even peak capacity. If you don't have to design your system for a peak capacity, you can have storage closer to the user, so you don't have to have as big lines as normally. And the flexibility is about hours or days. So the market now today, this is stationary storage market. This is not electric vehicles. This is a much smaller market, but it's big. So today or last year, it's about $71 billion market. Projected to be $870 billion market in 10 years. And the split today is that the lithium is dominating. About 75 plus, maybe 76%. And then you have the lead acid, this is the blue one here. And you have sodium, sulfur, and others. But we are mainly targeting with our aluminum ion batteries. Now we're just targeting the lead mainly, but it's also good to take a little bit piece of the lithium cake. Yes, and you see this is about 12 times bigger. This is a compounded annual growth rate. It's about 28% per year that this one will grow for 10 years. It's a huge increase. So can we continue with the current battery technologies? And if you think of the lithium and if you think of lead acid, and we look at this, and this is just a little bit mixture of everything. For example, lithium is made from a rare and hard to access raw materials. We're looking at unprecedented increase in mineral extraction because we have more than the stationary market. Lithium will at least increase by 42-fold, copper 21, and all the other rare materials. For end of life management, today about 5% of lithium ion is recycled. It's very difficult to recycle lithium because normally when you recycle, they want to shred things, but lithium batteries can explode. So you have to carefully open them, and then it's a very time-consuming and dangerous process. So only 5% is now being recycled. Toxic raw materials, lead, for example, lead acid, it's a big problem. It's there is money in this. So we can see a lot of photos, for example, from India, barefooted people just taking away the batteries. This is not good for humans. Risk of fire and explosion in lithium, failing to operate safely and damaged. You cannot really ship, for example, lithium batteries in planes. It's a really problem of transporting them. And yes, the toxic material are not good for us. We have issues of human rights violations. For example, we have from Democracy Republic of Congo. They use a lot of children there, manual labor. There are political risks. Lot of these materials come from countries that are not part of Europe. See here, this is the cobalt. Most of it comes from Congo. It's a very unstable political area. We have Russia, China, Chile. So most of these countries are, you see, Europe is not on the map. Same with here with copper, nickel. Yeah, okay, Russia is Europe, but you can see where this is. This is a different part of the world. And we would like to change that. So why not bring it more closer to us? Continuing a little bit here, see, this is projected. This is not for stationary battery. This is just in general. So this is the demand for lithium. This is the current mining. This is the mining now in construction. And this is projected. Of course, they can go off a little bit in the projection, but this is so far away that you will probably see the lithium prices go skyrocketing, even though you've been seeing lithium batteries going cheaper now. But you cannot really offset this if it really becomes over demanded. Okay, so basically what you can say, current battery technologies will not be able to rise to the challenge. So what can we do? What do we want? I listed out all the properties we would like to have. This is my wish list. I would love to have the future battery made from all natural materials, made from easily sourced materials, should be sustainable, we should be easy to recycle them, made from non-critical materials, so it should be easy to get them, and without any toxic heavy metals, without safety issues. For example, we don't want them to explode or catch fire, preferably with a longer lifetime that the current technologies have. Recycled percentage should be more than 95%, preferably. And all these objectives that we have, the Green Deal objectives of Europe and all that, we want to comply with that. It turns out aluminum ion meets most of this. So what is made of? It's the electrolyte is a urea with a mixture of aluminum chloride. The separator is a glass fiber, and the anode is aluminum. The cleaner, the more pure the aluminum, the better performance we get. We can use aluminum made from, let's say, 99 points, something less. And the cathode is a slurry. I'll tell you about that in the next slide. It's a mixture that we make, that we put on a graphite paper and dry it there. Yeah, so the slurry, it's a mixture of carbon black, hexagonal, molybdenum trioxide, and sodium alginate. Special blend, and we are still figuring out the best ratios. And our specialist at the University of Complutense in Madrid is always coming up with a little bit better performance. Yeah. So when we assemble the batteries, so this is actually post-mortem analysis of a battery where we put two little electrolytes here. So the electrolyte, when you put it in, it's made in glove box. Now everything that we do now is handmade, like Christmas decorations with scissors and stuff. So, but still we're getting good performance. We will get better once we get more stable production. But yeah, so we put two little electrolytes here, but it's thick. It's like gel, and it will become liquid once we train the battery. And so you need to train the batteries. We call it formation or activation, because we're making solid electrolyte interface between the carbon and the electrolyte. And this interface is very critical to the performance of the battery, both the lifetime and performance. So here you can see this is the formation process, or at least snapshot of it. With the blue one here, we start to just freshly assembled cell. We start to charge, we charge it up to 2.4 volts, and then we discharge it down to 0.4 volts, and then we charge it again. And you see the blue ends do not match. So we need to do it again and again, about 5 times, 6 times, until we get a continuous curve like the red one. That means we fully activated the battery and we can use it. And that at that time, the electrolyte is more fluid, and we have this solid interface, electrolyte interface. And this is actually a field of study now for also lithium, how to do this so that you can guarantee longer lifetime, better performance, and so on. So this is, there are some PhDs working on this. Yeah, a quick comparison. So here you're comparing the aluminum ion with the lithium, nickel metal hydride, nickel cadmium, and lead acid. And it's always nice to have, we are all green and they are a little bit less. Everyone has the problem. We have problems, but we omit them here. So now we look better. The main problem is we are still in prototype phase. So we are dealing with a lot of practical stuff. What we did, we made 2 usage scenarios. One is like UPS as a backup power. And one would be a battery that's used with solar cells. So basically, this one is like a constant voltage charging, and this one is constant current charging and discharging. And I want to show you a little bit interesting results from this. Yeah. So what we did was, for the UPS, we charged the battery for 2 hours at 2.2 volts. And then we discharged it for 30 seconds. This is like the backup power center. Okay, it's full, it's waiting. Suddenly, yes, we need to back up. And we use this 30 seconds. This is one cell. That's why we're seeing low numbers. So one cycle looks like this. Blue one here shows that we go up charging at 2 volts, and we keep it at 2 volts, and then we discharge for 30 seconds. The red one here shows the current. And this is an indicator of the self-discharge. So how much current do you need to maintain the voltage? And this is pretty low. This is about 50 milliamps. And then we did again. And every vertical line that you see here is the discharge. So what's interesting to look at is the voltage at the end of each discharge session. The batteries can go down to 0.4 volts. Here we are only seeing about 1.65 volts. So we have a lot breathing room. We can go for a longer time, and this is very promising. Interesting is that you see this fluctuating. You would think that they would degrade like exponentially or something like that. I'll come back to that later. Yes, and again, the red curve here, this is indicator of the self-discharge. This is just basically what we need to maintain the fully charged. We are, with our prototypes, we are stepping out of the classic battery chemistry testing. So this would be like when you're developing battery chemistry, you do it in something like this. You put the chemistry inside this and you test. But now we're starting to make cells, put cells, so that we are dealing with a lot of practical problems. Yeah, so the PV test, now we charge using 200 milliamps. We stop charging when it reaches 2.4 volts and a little higher than before. And then we discharge using 200 milliamps. And then for each cycle, we get something like this. Red one here shows we are charging here at 200 milliamps. Red one here shows we are discharging at 200 milliamps. And then we see this is the charging voltage because we keep the current fixed and then the voltage goes up. And we stop when it reaches 2.4 volts. And we discharge and we stop the discharge when it reaches 0.8 volts. But the battery can go on down to 0.4. This is one cycle. Then we do it again. And if we plot all of them together, we get something like this. Those are all the cycles that we got. And yes, at the bottom here, I'll go back one, it's less busy. Where the blue one here, the voltage hits, it's 0.8 volts. This is where we measure the capacity of the battery. Okay, so the end here shows the capacity of the battery. And when we do it again, you see that the capacity is changing. Goes all the way here down to 10 from, can't remember the number. It does not really matter, but you see it's changing. And you would think that at first, okay, it's just degrading. And it starts here, and just over time, it goes here. Not quite like that. This came just as a surprise. I mean, we knew a little bit, it was a little bit fluctuating, but when we plotted this capacity as a function of time, we saw that this is the capacity as a function of time. And you can see that the capacity during the first cycle, it is adapting to the load. Okay? And then it starts the degradation, but you see the degradation, there is some self-adaptation here. Some people like to call this fancy name like self-healing, and that's a very nice property. But this one is autonomous. We are not controlling it. It's just doing it itself. And we are not adding anything special into this. So that's why you can use the fancy name of intrinsic autonomous healing properties. But this is super interesting, at least because it shows that the battery is trying to adapt and trying to fix itself, meaning because we are getting a lot longer lifetime in laboratory than we are getting for lithium and lead acid, which is one of the properties that we would like to have for the future battery technologies. Yes, I think I'll stop here and maybe if you have questions, I can answer them, hopefully.
We have any questions?
What is the timeline for working battery right now?
Well, it depends if you're asking me. but you're asking the startup company that I'm working with. They want to rush things. I want to take things slower. But they want to be in 2024. They want to have the first commercial prototypes, at least with selected customers. But that means they need to set up the plant, manufacturing plant, because you will not sell handmade stuff like this. It's okay when we are testing this, but you need to buy the equipment to make this like every cell almost identical. They bought some equipment, but it's not been commissioned and not ready to use. But it's also raising money, and there's a little bit of reluctance in investors to go into other. They're still investing a lot into lithium because they know lithium, even though they know that the prices or the availability could be difficult later. But this is a little bit unknown, so you have to have like high risk, high gain investors.
There's one more question from the back.
Yeah.
Thanks for a nice presentation. I'd like to ask about your data analysis or simulation process. Have you tried to use the electrochemical model, or let's say some other models like this equivalent current model, just to simulate the process and somehow to analyze the state of health, or some other states used for analysis of batteries?
No, not really, because I'm coming in. I've been on this since 2020. They started earlier. They started, I think, in 2013, but they've been working in this environment. So what we're trying to do now is to make batteries, and so that's been my biggest headache now, is just to have battery cells that I can test, because I don't like just to test the chemistry. I want to go more into products, but once we are there, definitely we will go into all kinds of state of health maneuvering. And what we are planning to do, because you want to make the battery of the future, and I skipped that part really. I can go way to my first slides. I mean, when you have a system, something like this, batteries, yes, those are the big bulky part, but you have all the electronics and you have all the software that you need for controlling this. And you need sensors, and you need all kinds of prediction algorithms for state of health, state of charge, all these condition monitoring that we will need to have. And for future batteries, this is a huge investment. You want to know the status of this, and you want to be able to take actions way before things go wrong. So we will go there, but we are not there yet. What they have done is some modeling of the chemistries, but that I've not been involved in that.
Any more questions? Yeah, there's one more.
Okay, short question. You are using for cathode slurry and graphite paste, yes?
Yes.
It's very interesting. Maybe it is possible to use not so aggressive this liquid.
So the biggest problem that they dealt with, and most of their time went into, was preventing corrosion problems inside, because the aluminum, of course, oxidized. But they removed all the moisture. And so using the urea, and this is the result. So this is not my work, but this is what I get into my hands to test and try to be working on making a product. They published some papers on this. You can find them, and with a lot of analysis and studying. And it is working, but sometimes, for example, those are prototypes. So I try to solder the tabs. And when you solder the tabs, you a little bit affect the plastics, those plastics here. So the tabs are here going into the plastics, and then this gets hot. It opens up a pathway here. So if I leave this for, let's say, 2 or 3 weeks, and come back, the urea has a little bit leaked out, and you can see all this growth of crystals and stuff. And it's like, what's happening here? Because the moisture in the air is reacting to the urea stuff. But yes, they could probably use something else, but this is something that is working, and it lasts as long as there is no moisture coming into it. Yes, there will be a reaction to the urea, but there will not be like spontaneous, uncontrolled reactions that you would have if you had, for example, a leaking butter. That's like an explosive reaction. Yeah. All right.
Thank you very
Thank you.
much. Again.
Should you go to? Yeah, it's less using this. Off speaker over the show.
So for the next presentation, I welcome Dr. Christian Richter from University of Iceland.
We're almost set up. We are set up. Thank you very much. I said correctly that the right way to start is with a compliment and a joke, but I don't have to make it up. It's been wonderful. Our stay here in Lithuania. People are so friendly. The weather is so good. The cities are so beautiful and green. You don't even feel like you're in the city. So I guess, will that do, Einars? But no, I don't have to make it up. It's genuine. I actually have two talks here that you can see, and I probably will just give the first one. I wasn't sure how interested people are in the topic, but from a little bit of talking, it seems very much so. And I would, everybody have their own style. I really don't mind. I have to have a little bit of discussion, and I'm already the third one talking. It will help to keep you awake. So you can actually interject or have a question sort of in the middle. I will try to manage time. Primarily, I'm going to talk about e-fuels, and primarily I'm going to just talk about our experience in Iceland, because I'm not sure I'm qualified and wouldn't pretend to know the answer for everybody, but I have found that we as human beings are actually a lot the same, and our situations have always a lot of overlaps, more than we realize. Details are different, but there's also a lot of similarities. Here's Iceland. Welcome to Iceland. As you can see there in white, we produce about 20 terawatt hours per year of electricity. It comes roughly 75% from hydroelectric, 25% from geothermal. And as you've heard in the first talk, what do we do with it? Mostly send it to smelters. Ruan in the talk showed you nice pictures in fjord. It's really beautiful settings for these smelters. The guys have lunch and they look at volcanoes and glaciers. So it's really actually a nice smelter to work at. So we have 3 big smelters and 2 big ferrosilicon smelters. And now what I'm basically I would actually like to give you a chance to discuss and get your feedback. We can together consider Iceland's situation and think, what is our opinion? What should we do next? I'll get into a little bit more detail in a moment, but we can choose, if we want to diversify a little and add in the next 5 years a large e-fuel plant, or we can choose not to do it. So this is really what this talk is about. And on a deeper level, it's about the value of green hydrogen in Europe and the world today. What should we do with it, and how valuable is it, etc. So these are some themes behind the story that I will just tell you of this choice. So this is what I'm going to have all of you discuss a little bit, but to put it more precisely, in the politics in Iceland, in the newspapers, or if you talk to professors in the university, or sometimes even people in the coffee house or the bar, there is 3 things we could do. The first thing is we can keep this 20 terawatt hours per year of production, roughly the same level, and we can just keep on making smelting aluminum in ferrosilicon. That's one option. We can, if we want, add 1 to 3 terawatt hours per year of extra green energy production, and we can have a commercial e-fuel plant. A little bit more detail, but we can really do that, as I will convince you. Technology, capital, everything is there. If we want to do it, no problem. We just have to decide this is a good idea and get past the obstacles, which I will talk about a little bit too. But they're not major. Or the third one is we could, and this is many people think we should do this. We could take energy from one of the smelters, or a little bit from all of them, and get the 1 to 3 terawatt that way. So we don't have to build a new dam. We don't have to do any wind or anything, and we can give that to the e-fuel plant. So I'm going to do. I know it's a slightly unusual thing. Give you guys 30 seconds. If you're close enough to somebody, discuss among each other. We can maybe have a vote here. What do you think? If you were at Icelandic government and university asked you, give us advice. What would your advice be? Which way should we go? And please just quickly talk to your neighbor if you have one. It's very quiet. When I do it in class, the students are always willing to talk. But maybe they're not talking about what I think they're talking about. Okay, maybe I'll ask a quick question. Does Lithuania have similar choices to make? Or does anybody know? Do you have, or is it clear to Lithuanians exactly how much green energy you should produce and what you should do with it? And nobody wants to speak for Lithuania, which is understandable. Okay. Hopefully you guys have sort of, at least if you sat still and you have an idea what you think the answer should be. This what I put here is me, just as my feelings, my intuition as to I'm trying to predict the future. I think the most likely outcome from just having dealt in this sector and being part of an e-fuel development project, 65% chance we're going to do the first one. We are not going to make new energy and we're not going to have an e-fuel project. I think that's about a 25% chance, which is amazing, that we will have one of the world's first. There are several projects in development now. Nobody can see the future, but we might. And there's a 10% chance that people will take energy from the smelter. And then over here, I just basically did something we don't often do. I said what I think is the right thing to do. And technically, you can see I think the right thing to do is to build a new dam and add some wind and have an e-fuel plant. But usually we put 100%. And I tried really hard to think, okay, what's the chance I might get wrong? And this is what I think. Maybe I'm still overconfident. And there are people who really have the 100% somewhere else. Okay, so let's get into the details. Just as to you know, Gunnar told a little bit about himself, why, how much you should or should not listen to me. I am mostly like most of you. I'm just an academic. I've spent time in chemistry and physics, I'm a chemical engineer, my PhD in professor of chemical engineering, but it so happened that I was working on catalysis and material science in the physics labs in Northeast in my PhD, and in Yale I was in the Department of Chemistry. So that's my background. And I came to Iceland in 2016. I was a professor in the US until then for 7 years or so. And then in Iceland is where I was already working in this area, but academically, where I basically, it's a relatively small place, got contacted by 2 or 3 of these e-fuel projects. And I got really involved in one, and I'll tell you a little bit more. And so there's really, from that perspective that I'm saying the things I'm saying now. And it's a really interesting thing because you get the chance to work with Ministry of Energy teams, the people that know all the rules for carbon accounting, so the environmental agency, also the people that goes to Brussels, help write the rules. You sort of hear a little bit about that process. And then, of course, on the technology side, the project I'm working, the main technology partner is Siemens, doing the engineering, the front-end engineering studies, and then for carbon capture, Mitsubishi Heavy Industries for the catalysis, Johnson Matthey. And then, of course, you also get to go to all the smelters. You see all the emitters and where you would like to tap in and get CO2, for example. And finally, finance, you talk to the money people. So that's, as a professor, and some of you, I walk around you, you're in similar situations. Lithuanian power company or government may knock on your door and talk to you a little bit. Okay, so just one thing, just so you can see, why would we, it could be that Iceland is so weird and different that I'm wasting your time, but I think it's actually a good case because we just have 350,000 people. We're twice as big as Lithuania, but not quite, but it's by engineering approximation. So less people, more land. So land is not a problem. We have used, people estimate roughly 50% of our hydroelectric capacity are usable. So there is more if we want it. The geothermal only we used about 30%. And wind, we've just begun. We've got 2 turbines, and there's a lot of potential for the turbines we have. The capacity factor, Runar, what would you say? They tell us 44%, meaning 44% of the asset. If the wind will always be blowing, it will be 100%. And the wind developers they claim it's the best in Europe. They claim it's better than offshore in most places in Europe. So, and that's for onshore, which is a lot cheaper. So it's truly perhaps, and then finally, I think for all of Europe, the best water situation, really, it's abundant. So if you're going to ask where in Europe should we build our first e-fuel plant, I think the answer is kind of self-evident. This is the best spot for it. And yet, as we will discuss today, we will not necessarily, I put it at a 25% that we will do that. So that's sort of interesting also just to ask, why is that? And sometimes it's good. Look at your best location. If you cannot make it work there, then maybe you cannot make it work anywhere, or maybe you can learn something from it. Anyway, so that's sort of just why me and why Iceland? What possibly could I have to say, and why could we all learn something from this case? Okay, so now what I'm going to do is I'm just going to sort of quickly tell the story that will get us to sort of the conclusion. And this is like these movies where they have a scene and then they say Bucharest 1945, and then it jumps to 97. There's like 4 snapshots, but I think to sort of tells the story of e-fuel. If you're a real expert, maybe some of it will be old news to you, but I think it will help everybody to get sort of flavor for why we have an opportunity or not. And so I think that the first thing that I like to refer to people, because you can see if you can learn something, is we go to the United States in 2005. This was the president, and it made a big change because they made a law which mandated that the fuel companies in the US, ExxonMobil, Shell, BP, blend up to 10%, eventually is what it is now, of the fuel should be ethanol, corn ethanol. And the interesting thing is just the thing we as humans just watching this could have learned is that change can happen very quickly if you make a rule like that. You tell the oil companies you can sell in the US if you want to, but you have to. It happened. It happened extremely quickly so there was ethanol in the US since the 1970s, but going up that every station was E10, and of course now in Europe we have B7 and similar blends. It can happen quickly, and yes, this is the first point. So it's not so inconceivable to have a quick, large penetration. I think that's why, even in the United States, before anywhere else, which is usually slower. Of course, as we all know, the big difference is in the US legislation, it was a mandate by volume, just gallons, like they say in the US. So they didn't really matter, and you can find many analyses depending on how you form the corn, how you distill it. It could be even more emission than the fossil fuels. So this is not built into the crude US system at all, but it was able to move very fast. And now you have a massive industry. I think this is the main point I'm trying to make. Just like Runar was making a really good point that there's probably going to be a stationary storage large industry coming quickly. There was a large industry quickly. And it looks to many of us that we're on the verge of something similar in Europe. We have just moved a lot slower, and that will be one of our snapshots. But we have now similar mandates kicking in. And the big difference, is, we'll get to that, is unlike in the USA, where it was just saying 10% of the volume of in Europe would be liters that you put into your car should be ethanol. The European mandate is much more sophisticated, but it is aiming to not make, let's call it the mistake the US one make, where the fuel could actually be dirtier than the fossil fuel it replaces. That is what the European Union complicated rules try to make impossible. Okay, so what's the point of this? Why do I do this slide here? Okay, yes. So next, let's talk about, we're talking about the ethanol. This is not necessarily always, it could be, it all depends on how the ethanol is made, being that low CO2 footprint. So next I'm going to talk about e-fuels and just sort of explain the main point. And I think Runar made actually a point that I'm not going to make, but is the crux of it. And that is that even if we wanted to do everything in transportation with lithium, many people foresee on the horizon a significant problem with the minerals and the mining. We may not be able to. So the good news is that we do have a solution. And that is, we know in more than one way already, we have the technology fully developed to make the same fuels we have now, or fuels that work very similar, like methanol. You can just adjust the engine a little bit, or DME for a diesel engine. And they can be, we know how to make them carbon neutral, or even, I will tell you a little bit, carbon negative if we want to. So this is possible. And we have more than one way. We can do it from biogenic ways. Many of you in Lithuania are experts in that. Or we can do it in the way that I'm talking about now, which in the legislation have the funny title RFNBO, which means renewable, which stands for renewable fuel of non-biological origin. And the one that I will be talking about now is you take CO2 that you capture, hydrogen, you react it, and with 3 hydrogen molecules, one of them takes off an oxygen and gives you a water. The other two reacting with the remaining carbon monoxide gives you a methanol. So you basically from captured CO2 and green hydrogen, you can make it, just to make it concrete. But as you guys know, there's also other e-fuels, e-methane, e-ammonia, etc. But the main point I just want to make, and what is this? This is a YouTube clip you can watch, and it really attracted me because it insinuated it's going to tell you what is wrong with e-fuels, because there's always a catch, right? So I'm going to tell you what, you can watch this video too, it's quite good. It has one of the e-fuel projects in it. Let's see, what is the catch? On one hand, I said, no, it is the solution we have at hand, but there is a catch. And also, this is the crux of this video. If you were to spend the 10 minutes, this is what you're going to arrive at. They don't actually talk about the minerals, but so what I have on this slide, and there's many ways to do this, but this is sort of one of the nicest one. This is the car company Volvo have a car. I think I have, there it is. The Volvo C40 Recharge. So as far as I understand, this is an SUV that you can buy electric, or you can buy it diesel or gasoline. I'm not sure, one or the other, but internal combustion. And it's eventually the same body, same car, and the only thing that's different is the transmission. One has batteries and electric motor, and the other one I have. And so basically, and then they did a very detailed life cycle analysis for the two options. And so it's maybe one of the best, but you can find many studies like that to give you an idea, how green is a battery vehicle compared to a combustion vehicle. And the result is here on the bottom. And over here is basically kilometers that you've driven the car, and over here is the CO2 emissions. And then this one here is the internal combustion vehicle, its emissions. And then this here, these different lines, is the electric vehicle depending on where you drive. So let's assume Latvia is an average European country. For example, you can tell me how wrong that is, then it would be this line. So first thing you see is that when you buy an electric car, of course, as you all know, you have way more emissions embodied in the vehicle than you have in the combustion, because this basically the battery mining and production is quite a lot of emissions. It's about 0.5 ton per vehicle of CO2, which, if you know gas, it's actually a lot to have that. If you were to buy a new Tesla, you have 0.5 ton of CO2 that you're on the hook for in heaven, where they keep track of these things. It's just a joke. I don't know if they really do it. Okay, and then so then you drive your car, of course, and then if you are in a country like Iceland where the grid is completely clean, then this would be, you don't have more emissions because you recharge it from a clean grid. But here in Latvia, you would still have emissions because the electricity is not completely clean. And the takeaway is here, let's take this case. For example, you have to drive 77,000 kilometers, then you're equally clean than your neighbor who's driving a petrol or diesel vehicle. And then if you keep not sell the car and buy a new one because it's so shiny and nice, you have to keep driving that car, you can eventually get ahead. And over the lifetime of the vehicle, depending on where you live, you could have a 30% reduction or 50% reduction. Or if because we don't, and you can talk to Runar about this, but we don't know exactly how long these batteries will last and how long they will perform and when it will reach. Remember, he said 80%. If the battery reaches 80% capacity, we don't necessarily do this with our cell phones or computers, but then the car people say no, it's not good enough for us anymore. So we don't actually know when the end for the battery vehicles versus the internal combustion vehicles is. All this was sort of a very concrete, long way of just telling you that the batteries is not a 100% solution as it is in the popular imagination. I mean, this is just the reality. I'm not anti, it looks like I'm anti-battery, but I'm not. We should admit how much of a solution it is. And then the counterpoint is, in theory, at least, the e-fuels could be. If you were to fully drive on an e-fuel, you could, and I'll just take the methanol case because some people are fans of just pure hydrogen or ammonia because there's no CO2 in it. But I would say, for example, the methanol we plan to make in Iceland is very honest because we first take the CO2 from the air. So we pay before we play. Then we, of course, package our hydrogen with that CO2. It's just a packaging material. And then if you drive the car, yes, you put it back, but it's completely neutral as ammonia was the fuel, or hydrogen was the fuel. In fact, we prepaid. And what I show over here, this was actually made by George Olah, Nobel Prize winner, who first proposed that we can use methanol to have a completely circular economy. But in Iceland, when we capture the CO2 from our smelters at the moment, in the future we can do air capture or something biogenic. Then, as a chemical engineer, how it actually works is you capture a whole bunch of CO2, and then you have to remove the sulfur to very low parts per billion because the catalyst we use doesn't like sulfur. And when you do that as an engineer, you usually get two streams. You get a CO2 stream with more sulfur and one with virtually no sulfur. The one with more sulfur is ideal for injecting. And it so happens that in Iceland, we also have a project quite famous called Carbfix, and we have got basalt rocks underneath, and we've shown that if you inject into those rocks, the CO2 essentially becomes rock within about 2 years. So it's actually, when you do the two things together, so the short of it is, if you want to try to build a capture plant just to inject, it's too expensive. But if you want to build a capture plant to make e-fuel, you get a waste stream that you can easily inject. And if you do that, you can actually have a carbon negative fuel. So this is just to say, and from this perspective, e-fuels are perfect. It's the perfect solution. But there's a catch, of course. This is the point. We'll now get to the catch. And the catch is quite simply this. See which slide says that one. Not really. Okay, so I think this is the best slide I have for it. The catch is that we need a lot of energy. E-fuels take a lot of energy. This is just a slide to show you sort of this is the mix of Iceland. This is hydroelectric and geothermal. And I used to, when I give talks, add other countries, but I think Iceland produces about 20 terawatt hours per year of energy. Lithuania about 4, so it's actually less. So it doesn't work so well. But so it would be sort of struck to put it here. But this was, for example, I gave talk at ETU. So this is the Danish and the TUE for the Netherlands. And so you can see if you want to build just one e-fuel plant, so the minimum commercial scale is about 100,000 tons per year. This is how much energy you need, how much clean energy. And so in terms of Iceland, it would be a 6% increase. And the plant we would really like to do would be about 300,000 tons. That would be really profitable. But that's about 17% of energy capacity Iceland has to add. And this is for these countries, how much they have to add in terms of what they generate. And I realize I should actually, because this has to be green to be eligible e-fuel. So this is a mistake I made here. This is how much of capacity Denmark or Netherlands have to add above what they generate now. But I really should have said about the green stuff they generate. Anyway, this is this, my main point here is just to say this is the catch. There is no other catch. If you also watch the video, they will say that we don't have enough energy to do this. This is the catch. And what they say then, of course, is, and you will also see if you watch the video, the Siemens is also involved in another project that's in Chile. So the idea is go to places like Chile where there's big Patagonian valleys and lots of wind, or go to the Sahara. This is sort of the dream. This is the only way we could really fulfill this. Find these large expansions you would need. Okay, but it's interesting to ask, why do we need so much energy? And the answer is quite simply, it's not a mistake, it's not a flaw, it's because we are trying to replace oil, natural gas, and coal. And that is just chock block full of energy. This is like full of calories, like the worst chocolate bar you can eat. You immediately become fat. And we are trying to replace that. We are trying to make that. And this is the amount of energy that's in it. So it's actually not a flaw. I used to give the talk and also talk about that electrolysis, splitting water into hydrogen and oxygen is inefficient, but to cut time, because I'm sure it's I'm already moving along. I will not keep this, but we can have question and answer on this if you want. I am beginning to think as I get more mature. And so I used to have 2 points that we need so much energy because we are trying to make synthetic oil and there's a lot of energy in it. First law of thermodynamics. We're scientists, you cannot get around it. If you want to make a synthetic oil, you have to put as much energy as in there. And that's the real reason now today, I would say. I used to also say electrolysis is about 55% efficient because by the Gibbs energy, we use about twice the electricity. But as I understand more and more of engineering and maturity in it, I realize that our room for improvement in electrolysis is not much. I think we can be about 15% more efficient with solid oxide electrolysis. That's high temperature, 800 Celsius stuff. And then something I was personally working on a little bit is if we just do maybe intermediate temperature electrolysis, that's not so famous, but I think it has more potential. So do electrolysis not at 90 Celsius, as current electrolysis run, but at 200, then I think we have about a 20 to 30% improvement. So in short, yeah, it's true. We could perhaps do a little bit better with e-fuel by making electrolysis more efficient. It's way more efficient than, sorry, I thought Ruan is sitting here, but that's it. Than aluminum smelting, for example. That you could see for Ruan's number that aluminum smelting is less than 50% efficient. But so electrolysis, splitting water into hydrogen, is much more efficient than, for example, making aluminum. But I don't think there's really practically that much room for big improvement. So the bottom line is, if we want to do this, we're going to need a lot of green energy. We will eventually have to figure out how to put solar panels in the Sahara, or solar thermal in the Sahara, or lots of wind thermals and turbines in Chile. Okay, so that was the point of this. What the only catch is that the decision in the beginning. If we want e-fuels, we have to build a dam, and maybe not everybody wants to build a dam. This is just the part of the story where I'm going to show you that there's no technological barriers. This is a snapshot. So now we go to Reykjavik, 2008, and these 3 guys, actually, he was not yet in the team. They were drinking buddies, as you could see. This is sort of the professor guy, physical chemist from University of Iceland, Otto Ingolson, who was one of the people that recruited me to the job I'm in now. This is an American, a mechanical engineer. And this guy is a business guy, Icelander. They both are pilots, and I think that aeronautical engineering, actually, I think they studied together in the US. That's how they became friends, and later they hired a CEO from MIT. So they had this idea to make e-fuels already in 2008 when it wasn't really so hot, and they were drunk enough or crazy enough to execute. And so the result was this plant that you see over here, which was the world's first CO2 to methanol plant in Iceland. So they started the company in 2008. They did some experiments downtown Reykjavik in a little lab, and then there were a financial boom in Iceland that also crashed, unfortunately for them, but they were able to get enough capital together to, it's about 100 million investment of euros that it took. They built this plant. Just to show you in the slide, there's Reykjavik, there's the airport, and there is the Blue Lagoon, which if you visit Iceland, you might highly recommend it. What people don't know is that what the Blue Lagoon is, it's actually the effluent from a power plant, but very cleverly, these rocks are high enough that if you're in the lagoon here, you don't see the power plant. So you won't even know. And you will imagine it's natural, but technically it's steam to make electricity. It's still from Earth. It's still full of silica, it's still healthy, but the tourist just doesn't like to know it's power plant effluent. Anyway, so the reason I'm telling you all of this is because that's also where the world's methanol plant is. And it's not a coincidence, because this particular plant gets its CO2 from the geothermal plant. Not many people know this, but if you drill into Earth for steam, every well is unique, and some of the wells have some CO2 in there. And then those CO2 is actually relatively easy to extract. It's just water condenses out easily. So it was a good CO2 source for the first plant. It will not be a good CO2 source for our bigger plant because there's not enough. And this is just sort of basic flow diagram for the process. I'm not going to spend a lot of time. I just want to give the main idea that I already sort of spoke very quickly. That is essentially a hydrogen plant. So water and clean energy and electrolysis. The carbon capture plant, you compress the two. I should have put a number here. It's 80 bar. You compress it to 80 bar. The current catalysts are really good. The selectivity is more than 99%. What that means is you don't have, if you pick the right temperature and pressure, which is 80 bar and 280 Celsius, this is alumina, copper zinc oxide and alumina, or CZN catalyst, very well known for methanol synthesis, commercial methanol synthesis from natural gas, been used for decades. So it's just a slightly modified version of the same thing, and it works perfectly. My message is just to show you that there is no technological gaps. Unfortunately, I guess if you're a scientist, but there is many other things to do, but not in terms of this. And by this, I mean taking CO2 and hydrogen and making methanol. And there's always small improvements. What I mean, there's no major barrier. And of course, then what you end up with, if you do this reaction, CO2 and 3 hydrogens, one of them makes a water, one of them makes a methanol. So you have very, very nice for a chemical engineer to simulate. You end up from the reactor with a mixture that is 50% by molecules, water, 50% methanol. So then, very common, you need 1 or 2 distillation towers, 2 that's integrated, and you get high-grade pure green methanol and water that you can actually even, if you like, reuse. The German engineers would let you, if you don't like impurities, into the electrolytes. Well, what I mean by reuse, recycle and split to make hydrogen. Okay, so this is just to give you a gist. There's another snapshot that this can be done. This plant was built, it operated for a decade, from 2012 to 2000. Sorry, the numbers is here. It produced 4,000 tons per year of methanol. Technologically, of course, always you learn lessons. The compressor is important, or this or that. But there were really no problems. It was a success. It stopped operating because it's not financial. The company, the guys called their company Carbon Recycling International, or CRI, and they called this very generally. I never liked it. They called it a demonstration plant. I just wanted to call it the first plant. I would say big as a building, but they cleverly did, because they know it would not be economic. The idea was to scale up, but unfortunately, until now, and we are talking about now, should we build the scale up? And there probably will be scale-ups all around the world, because if you get a big enough subsidy from, like say, the US Department of Energy, then you can build anything you like. But this was without subsidy, and this is sort of what we also hope to do in Iceland, to build a plant that can support itself. Okay, so I think I want to move a little faster. This is not so important. This is just when I give this, people tell me, oh, but we did this, we did that. We at Switzerland, ETH have this little, and then I just try to show them that indeed the CRI plant is, compared to the biggest other thing that has been done before, much bigger. How much methanol it produced. There's the number of cars you can drive, and also it ran for a decade commercially, while the other stuff is typically, the EU gave us $1 million. We had enough to run for 2 months. So it's sort of why I think it is a milestone in the story of e-fuels, for sure. But if you don't sort of look into the details, many people say, no, you forget about our reactor. Okay, so so here's the key points of relevance for us today. There is no technological barrier. And so why was it not commercial? His name, so Iceland is small, so I know the sales guy. He's now the methanol inspector. His name is Matthias, and he could tell us that roughly average about 600 euros per ton for his green methanol. The fossil methanol is 400 euros per ton. It fluctuates, it's a market, but that's roughly the average. And as you will see here, I'll show you just quickly the cost of production. It's about 600 to 800. So obviously, I should just quickly talk you through what this curve is. It's a little bit important. Over here is the size of the methanol plant. This would be 1 million tons per year, which is how big commercial refinery fossil fuel methanol plants these days have to be competitive. And then over here, it tells you the cost in euros per ton to make the methanol. And then it's the different kinds. We have, of course, natural gas, which is by far the cheapest. You can make it from coal, which is mostly done in China and South Africa, where I grew up, because the coal is what they have, and they want to be energy independent. As you will see, it's more expensive. So let's just draw some lines to the data points. These are, of course, actual plants. as far as data is available. And my main point of this, you can see there's an economy of scale. And then I will just put on the slide, this is where the CRI plant is. It's too small, you can see. Hence, it's too expensive and it wasn't economical. And so what we really want to do now, we are talking about, now you can see why I say about 100,000 tons, but people just know it from experience too, is when you get most of the economy of scale benefits. So this is really what you have to be if you want to be profitable, and you'll be sort of really profitable if you at this scale. So this is really just the point of this slide, telling you what we have learned in terms of the economics and why we think, you know, this is 100 to 300,000 is the right size, and that it is actually promising. And you can sort of see the cost of production. It's still, unfortunately, and there's no way, I wish there was a way to make it cheaper than fossil, but it's not. It's about twice the price. And even more expensive than the coal. Although the coal is not far, and the coal is in some sense political, that people use coal for making methanol. Okay. So now the next snapshot, the important one, and that's the biggest one. So basically we see that we could, by having a bigger plant, bring down the cost of production. It still is difficult to pay off the loans and everything at 600 euros per ton. But what I'm going to show you now is that we anticipate, because remember in the US, there was this fuel mandate and suddenly there's this ethanol industry. In the EU, the same thing is happening right now. And the nice, two things are good about the EU laws, although it took, 2 decades longer than the United States to have a blending mandate, but there is some good features to it. And that is, this is not even completely up to date, and just the best infographic I can show you, but the principles are still in the latest version of the European legislation that's bringing about this blending mandate is still the same. And what it shows you here is that when it comes to the reduction that all the European countries in transportation CO2 emission will have to achieve, there is subcategories that kind of pushes the member states to achieve it in a specific way, and that includes that there is subcategories for biofuels, of course, and then also for this type of fuel. So it's a long way of saying that if BP wants to sell in Germany, there will be a requirement that some fraction of that they show a CO2 reduction in their fuel, number one, and it is going to increase year by year. And secondly, part of that reduction has to be from fuel, like what I just explained about. And then the crucial point is, unlike in the US, it's not per gallon that they have to show that, it's not just BP should have 10 gallons of biofuel. No, BP should have 10 gallons of, not 10 gallons is not the word. They should achieve a certain CO2 reduction per megajoule of energy. And the point is, it really favors a fuel like Iceland, because now one gets rewarded for having a fuel that's truly carbon neutral or even carbon negative. It has value to BP. If they use Icelandic e-fuel, they can put in less and get the same compliance with the government because they have the CO2 reduction than somebody who used, ethanol from Brazil, where the CO2 reduction is about just half as much as fossil fuel. Well, with our e-fuel, it's almost nothing compared to fossil fuel, or even negative. And there is value in the new legislation. And it's sadly kind of complicated because it makes it hard to pitch it to investors, but every fuel in theory and in practice also, when you talk to the trading desk of BP, could have a different price because it has different value. And when you use the estimates for what this price will be, and sorry, there's a mistake on the slide. If you're a mathematician, you would say, okay, that's just a number. So this will be 1,200 to 200. This is roughly the estimates, and I know it's a bit crazy, but to people who are used to selling at 600 euros per ton. But within this legislation, if you have around the 2 to 3 grams CO2 per megajoule carbon footprint, where for fossil fuels it's 96. So it's almost 100% reduction. This is roughly the value we calculated will have to BP within the legislation. And that is my main point. That is way, way above the cost. That is extremely profitable. Okay, so that's the main point. It really does appear that within the next decade, because of these laws which are now being finally adopted, this could be a profitable business. Okay, so let's just go through this list. So is the technology ready? Hopefully I've convinced you by running a big plant, bigger than anything usually done at the university. Big as a building for 10 years, that the mature technology is mature and ready. Is it profitable? I try to make the argument now. I think it's true. Sounds right. But I don't think I'm bullshitting. You know, if you pitch in the US, there's a whole culture in Silicon Valley of pitching stuff and exaggerating. I don't think I exaggerate, but maybe I'm a little bit influenced by that. The capital, okay, this is the small thing. So the project I'm involved, Mitsubishi Corporation is one of the people that we've predominantly been talking to, and they signaled that if the fuel is there, the fuel, the renewable energy, and it's within a certain price class, which it currently is in Iceland, that they would be able to provide 30% of the cost to build such a plant. So the cost for building a plant on the scale I'm talking about is about €500 million to €1 billion. And when I first heard these numbers as a professor in 2018, I thought people were going to think I'm crazy. You think I'm crazy? You already think I'm crazy. But I got very used to these numbers now. For the oil industry, they do projects like on this scale all the time. This is actually not even, this is not super expensive. They do more expensive stuff. And I can just basically tell you, I've seen one example that many of these big companies like Mitsubishi or BP, they have big funds. We're all responding to the climate change, and most of these companies have set aside funds for green projects, and they're looking for places to put them. So it does not seem to be a major problem if you have the right project and everything is in place to get the capital. So the question is then, why do I think it will most likely not happen? This was a real surprise to me. And it turns out that many people are resistant, and that it really matters in having more dams and wind parks. And that it really matters. That was a surprise to me. In particular, in Iceland, the Green Party, which is kind of ironic. The conservatives are much more in favor of development. The Green Party believe either that we should just do something which they say is degrowth, we should somehow just all look less, do less, or they think it should be taken from the smelters. And I don't want to make a long talk, but quite simply, if you take production away from Icelandic smelters, it pops up somewhere else, and it could be in China, and the CO2 footprint of that is even bigger than anything we can save with e-fuels. So that's why I think it's not the right approach, although it might happen, because many people are in favor of that. They say, yes, we should have an e-fuel plant, but we should somehow take power away from the smelters. So this is really for us. I don't know how strong it is. Maybe not in so much in other countries. In Iceland, there's a little bit of a history too, because people did get dams, and then the energy goes to the smelters, and people imagine they're going to have more benefit, I think, than they see. I've been to all the smelters. Whenever I talk to the workers on the floor or the people that live near the smelters, they don't think like that. They're very happy that there's jobs, and there's usually development in the rural area. But it's people, the majority of people who live in Reykjavik, they don't think this way. Because they imagine the dam is so destructive, and they imagine that they don't see any real benefit. They perhaps correctly hear that the smelters are paying very little taxes, and then they think, oh, we did this, nothing really changed, so it's not worth the real and imagined destruction to nature. So that's sort of the challenge for us, and what will determine. Oh, I forgot to say this, and that's just the people, but even more important, because the main political parties in Iceland are supporting this. Oh, I forgot to say the split also, of course, exactly into Iceland's government policy, of course, because like many countries, Iceland's governing coalition as a charter, and they say number one priority in their charter is their climate change policy, and they have a goal, a certain reduction by 2030. And Iceland has the unique problem that we are so green, our grid is completely green already, that we are all of our emissions that people are responsible for, because the aluminum smelters and the European legislation, the Europeans use the aluminum, so that doesn't count under Iceland. So the only emission that Icelandic people are on the hook for are the cars they drive, the trucks that move our stuff around, and our fishing fleet. So this is all we have to reduce. And the only thing you can reduce that is by having a green fuel. So we would either have to import a biofuel at high cost or produce this. So there's a long way of saying that some of the political parties, including the somewhat conservative party, people will call that, are looking for a way to fulfill their promise, and they realized already, they have technical teams, that the only way they can clean up diesel trucks and boats is by putting a cleaner fuel into it. So it fits actually the government's stated policy. So the choice is just, we will not do what we said, or we do this. But still, we may not. So here's my final point. The other big barrier is actually the energy companies. So the biggest energy company is they're run by themselves, but they're publicly owned company. And those leadership in energy companies have a tremendous amount of power. In theory, I think it was worthwhile to tell you because maybe it's similar here. In theory, the CEO of the energy company gets appointed by a board, and the board gets appointed by the Minister of Finance, and the Minister of Finance gets elected by the people. But in practice, of course, the people on the board have been there for 2 decades and all know each other, and they're very influential and powerful and liked. And the CEO that have been there for 2 decades, and you can imagine what I'm saying. It's not really working the way it does in theory. The CEO of the power company and the upper management in this board almost, you guys took me to the Hanging Castle just yesterday. It's almost like a noble council. And they also are a major part. You know, who gets the power and how much new power we have. Anyway, you guys get the gist. I thought I'd just tell you this thing. This is one of the things that I found interesting. I thought some of the other things would be the barrier to these type of projects, but this is the real barrier. I don't think I will do this because I talked long enough. That was just a little bit about the collaboration coming here and similar to this, how we can make this what Ron introduced, taking the aluminum waste, as someone correctly asked, grinding it down to a small enough size, reacting it with water and getting hydrogen from that, how you can potentially make it economical. But within this scheme, as you could see, hydrogen could actually, in the right place, if it has the right green certification, have very high value within this upcoming legislation in the EU. And that creates opportunities for all of us in Iceland, definitely also in Lithuania and Latvia and so on, that I've seen the solar, the wind, and the biomass that you have. There's interesting ways you can combine it. And if, depending on your power companies and your situation, if you can move on it on time, because unfortunately, maybe I should just say this, it's not obvious to everybody. So for example, if you want to build a big plant like this and you want to produce on time for this legislation, we're talking about 26 to 27, then you need to start doing it now. It takes 4 to 5 years. That's very fast to go through all the engineering stages, all the financing stages to build a plant like this. And if you have to build a dam or a wind farm, then most people would say a decade. So anyway, that's sort of the things I think I have to share as a professor or researcher, like most of you who dabbled in the green fuel development project space for 4 years. Any questions?
Yeah, please. I don't know if it's working.
Don't give yourself.
Okay, so do you have any questions? Please wait, I'll give you the microphone.
Thank you, Anders. I like questions.
Great.
I would be sad if there was none.
Thank you for the presentation. Do you know how much biomass would be necessary to for such a plant and rough estimation?
Yeah, of course, I thought about it because we don't, for many reasons. So one reason is under the current EU legislation, you can use industrial emission like I'm talking about now until 2040. So even if you talk to the investors or if you're a company like this, it's 2040 is long enough away that you don't have to immediately know the answer, but you would have to think of it. And after 2040, you can use the dreaming that, and it may or may not come to be, but this is what the EU are imagining, that we're going to capture it directly from the air. Okay. Should I just wiggle it? Okay, this is the optional talk. Sorry, yeah. So that's something we need to think about, basically. Or you need to go biogenic. So this is what the EU lawmakers are imagining, that bio-derived e-fuels are good. Or of course, with many, it shouldn't be food, it shouldn't be this, it shouldn't be that. And so we have to think of it. So I sort of know, and the first thing I know is that Iceland doesn't really have any, ourselves, we don't have enough. Our forestry industry is very nascent. Okay, so I don't know really how to give you a quantitative answer.
I guess,
but I can tell you that Iceland do not have enough. We have hay and we have some seaweed thing we're trying to develop. But Yeah, how would, maybe I should ask you this, how would you expect me to quantify it?
I guess then if we want to participate, we should start growing some specific things. We have a lot of fields.
So maybe this is a good idea. So I can tell you how it could look. So I don't know, some of you may know this. So for example, there is this project, somewhat controversial for various reasons in the UK called DARX. The idea being that they import pallets of biomass to replace their coal. They used to run coal-fired power plants, and now they fire them with biomass. And of course, you guys know a lot about biomass power here. So that could be a way to do this, absolutely, with biomass from Lithuania. And the key question is always just you have to look at you really have to read all these long, boring laws and make sure that your biomass is eligible. Unlike the simple US legislation, the EU legislation is very dense. But for good reason, they want to make sure, for example, that we don't use the good part of the tree from which we should make furniture. But this is a big business opportunity for anybody, and this is not just Iceland. Also, the people in UK all around the world. If you can produce eligible biomass, and it's got the right, we just show you very good labs here in Lithuania, I'm sure in Latvia as well. If you have the right moisture content, ash content, calorific content to meet the requirements, and you're eligible under the laws, it would have very high value, and that could be the future of these plants. Absolutely, if industrial emissions is no longer eligible. We don't have a lot of time, but we can also talk what you will do with the biomass. Of course, there's actually more than one route, but it could ultimately be both an energy and CO2 source from which you can then make fuels, and we have the technology for that. Yes, I think that sort of was your answer. I couldn't tell you how many tons of pellets, although the answer, it's out there. It's not hard to come. Just don't have it on the top of my head.
All right, so maybe the last one. Then if I'm just graduating and I want some sort of direction with this.
I thought you're going to ask me for a job,
direction,
but it's not going.
No, well, there are plenty of labs, so
yes, job is not a problem. Okay. Yes. So to complete your question. Yes,
so do you perceive this as a separate additional possibility for new research, and how much research?
Yeah, so that's usually what I try to talk about years ago, and I, for example, said that there's rooms for improvement. So, of course, there's always process improvements everywhere. I was just trying to sort of say that, as far as I'm concerned, for example, making e-methanol, there is really no big gaps. And this is when I was in the US, especially at Yale, we always pretend that, oh, this is the problem. We made up the problem when we said we will research the solution. I don't think there is a big gap, but there's many small gaps. There's a lot to be developed on the CO2 capture side, for example. There's only one company, that's why we work with them, Mitsubishi Heavy Industries, who can capture and also I spoke to, you and Petrus, because you have gas turbines in Latvia. And the CO2 concentration from those can be as low as 3%. There's only one company, and if they didn't exist, there would be none that can capture, economically from that lower level, the CO2. That's the limit. And of course, the ultimate limit that people dream of is from the atmosphere, 0.04%. So that's a big area. And this is one example. So no, there definitely are also the stuff we are working on in this project, in the recycling sphere and getting hydrogen as in part of the recycling process. Just, what we've been talking about. We've uncovered some gaps, actually, so yeah. But sorry, I do admit that I also have the somewhat disappointing, I say, for a scientist, truth that we don't have technological gaps to do, for example, what I've been talking about today. There is no.
Yeah.
Can you explain to me when you talk about this? You're picking this up? Yes. No. Can you explain? I mean, so you talk about e-fuel, but there's not one e-fuel that fits everyone.
Yes.
You have heavy oils on the big fishing ships, very high density.
Yes.
Then we have the marine diesel oil, and then we have automotive diesel oil. Is that easy to adapt?
Yeah, I didn't talk. Of course, there's so many different talks one can make. But so the way the deployment would work, so methanol can be blended up to 50% with no modification, and that's been for some strange reasons, as Riley company is the big experts on this. But and it's been trialed in Italy on thousands of cars. So for gasoline, or what the Americans call gas, or the British call petroleum, I don't know what you call it here, for your gasoline cars, that's the first step, a blend. And every member state can choose if they want to do M5, M10, M3. You can begin to introduce it this way. That's the easy one. For diesel, it's a bit trickier. For diesel, the most likely route at the moment, and it's not as the so what I'm basically saying for blending into gasoline, it's 100% ready to go. The testing has been done, the fuel standard exists, everything. It's just the country just have to decide. We're going to make it legal, and we're going to incentivize or mandate it. For diesel, the route is most likely that you take the methanol molecule and you have one more reactor, you make a molecule called dimethyl ether. And the laboratory people feel that's much more blendable and useful with diesel, but it's not as fully tested and advanced in the fuel standards, because what we mean by fuel standards is the rules for the gasoline we put in our cars, but beyond it is also a whole process of because the fuels we put in our car is a recipe, it's a blend of many molecules. So you throw in a new molecule like methanol, then you need to compensate in the additives so that it meets many specifications. So, and that's not fully developed yet on the diesel side. So, but that would be the next step. In fact, we've been reaching out a little bit to people that can help push that as one of the producers. All the producers, of course, come together, and the oil companies will all have an interest in that. So DME blended into diesel is then the likely solution for diesel blend for automotive and also for the shipping. And then in the final long-term future, sorry, it's a very good question. Ideally, we all switch to. It's not a big modification, but with some modification, but nobody wants to modify the cars, of course, but future engines could be 100% methanol or 100% DME. Ideally, that's where we go, because these fuels are also less particulates, less SOx, less NOx. Basically, air quality and water quality is much better with these fuels than with the ones we currently get from the ground in Saudi Arabia.
Thank you so much. I see there's probably more questions, but we are running out of time and we have still one presenter. So thank you very much.
We are here more as well. So please,
yeah, so
please
after
talk to
the
us.
next presenter, there will be a break. So you can come to everyone and ask as many questions as you want. So for now, I want to thank you very much. And excuse me, wait.
Oh, really?
This is
Thank you very much.
Thank you very much.
Thank you.
Thank you. So, yeah. So now I'm gonna present the last presenter. It's Anna Pitlak from Polish Academy of Science, please.
I don't know whether I should still say good morning. It's maybe good morning. I'm aware of the fact that we are just before the coffee break, so I will try to be concise. And maybe I will be able to catch your attention, because the subject I will be presenting is a little bit different from what was said before, but maybe that's good, because we should, let's say, get out of our boxes. So I will be talking about methane. Why should we be concerned with the issues related with that gas? First of all, a little bit of introduction of my working place. I'm working at the Institute of Agrophysics, Polish Academy of Sciences. We are in Lublin. The city is something around 7 hours driving from Kaunas. And this is just, I'm showing this to you to encourage you to cooperate with our institute, because I think that there are several areas that we could find, at which we could find a common ground. The main objectives of our institute is to ensure proper conditions for cultivation of agricultural plants, ensure high quality of food and plant materials, mitigate the effects of climate change that are being forced by the agriculture, and development of circular bioeconomy. The institute employs about 70 scientists, and we have also several PhD students and postdocs, which I also encourage you to become acknowledged with, because we have often several positions to be taken, especially postdoc positions. So if somebody is searching for a place to develop skills or just to meet new people and to work in a very pleasant place, Institute of Agrophysics is certainly a good direction. The institute is divided into 6 departments. My department is the Department of Natural Environment Biogeochemistry. We're quite well equipped. Since we are working with greenhouse gases, we have several measurement techniques developed both for field studies and for laboratory studies. And our department, our team works in an interdisciplinary mode. This is because we are trying to explain processes that occur in the natural environment, especially in soil environment. And those processes are highly complicated. And the fact that we work and that our team is interdisciplinary is not the fact that there's a trend towards interdisciplinarity. It's just the fact that we're trying to answer some fundamental questions about how soil greenhouse gases emissions are being driven, what are the main drivers, and the team was the people that create our team were brought together to make answering those questions possible. So we have a section that deal with emissions. Some part of the team is working with soil erosion, and my part is microbiology. Methane cycle microbiology is my subject since the very beginning of my scientific work. First, I was dealing with microecosystems that are found in geological formations, but this is no longer my occupation. Now I'm working on soil peatlands, and my main research tools are from the molecular ecology. We use next generation sequencing to study the structure of microbial communities, but those results are not quantitative, and they only deliver information about what kind of bacteria are present in the soil, for instance. Therefore, the other applied technique is digital PCR, quite new technique, which provides strictly quantitative information that support next generation results. Results delivered by next generation sequencing. Currently, my main topic is the influence of anthropopression on biological methane oxidation in agricultural soils. And by this anthropopressure, I understand the use of pesticides. So this is my currently run project. The other scientist that is directly involved in greenhouse gases emissions from soil is Anna Walkiewicz. She's not here today, but her work is very important in our team because she works in the fields, in the forest, and she studies greenhouse gases emissions. And currently, she tries to recognize what kind of agricultural practices are able to increase methane uptake by the soil. This is in the framework of the European AirNet project. So that's for the introduction. Now I will tell you about the main topic of the lecture, methane. I'm sure that most of you know methane as an energy source, because this is how most of people recognize this gas. And that's exactly what it is. It is an energy source. However, methane is also very important compound in the nature. It was one of the first organic compounds in the world. It is the simplest gas, colorless, odorless. What's very important is insoluble in water and has very low density. Why is it important? Because methane is being often formed in anoxic environments, just like, let's say, in the anoxic part of the water column. And because it is so, it has so low density, it immediately migrates to the atmosphere. I think that all of you saw the beautiful frozen methane bubbles in the Baikal Sea. Those are pictures often posted as something beautiful. In fact, this is really threatening because that's exactly the methane emission frozen in time. Methane was discovered by Alessandro Volta, who exactly caught the bubbles that were released from the sediments of one of the Italian lakes. And I'm showing this picture of this article for one specific reason. I'm sure that all of us publish, and recently it became very often required to publish a graphical abstract for the publication. This is a general trend, and some people argue that this is quite difficult because it requires us to have some sense of the art to create a graphical abstract that is descriptive and also eye-catching. So for all those who claim that this is something new, I show this picture. This is the very first, I guess, graphical abstract, one of the first graphical abstracts, because you can see here Alessandro Volta catching methane bubbles. And this is from the 18th century. So graphical abstracts are not that new. Okay, so going back to methane. As it was already mentioned, methane is one of the fossil resources, very attractive fossil resource, because it provides a huge amount of energy per mass, per molecule. It is widely used for domestic purposes, for energy production, also on industrial scale. And it is also noteworthy that methane is a substance in many industrial processes in which organic compounds are being produced. For example, it is a source of hydrogen in chemical production of chemicals that are further used as fertilizers, for example, precursors of fabrics, or other highly used chemicals that are of everyday use, even if we are not conscious of the fact that methane-derived compounds are around us. It is. I'm sure that even the seats that we are sitting on have their covers made of, to some extent, from methane. Okay, but what is most important for me is the fact that methane is a greenhouse gas. And the fact that its atmospheric concentration increases rapidly. As you can see on this picture, the red dots depict the, let's say, last 200 years of methane concentrations in the atmosphere. And those pictures both are in fact very alarming. What's crucial It is the fact that this rapid increase is correlated with the development of industry, coal mining, and other fossil fuels extraction, natural gas extraction. All those activities lead to methane, to increase in the presence of methane in the atmosphere. Also, other human-related activities are increasing methane atmospheric abundance, but I will tell about it a little bit later. So currently, it is estimated that methane is being responsible for something around 20% of global warming. The question why methane is such a potent greenhouse gas is, of course, the answer is in physics because of the wide ranges of absorption in infrared spectra. But as you can see on this graph below, there are also other gases very important for greenhouse effect. So why should we focus on methane? Well, the answer lies in those numbers. First of all, methane has a very short lifetime in the atmosphere. Very short, of course, when compared to other greenhouse gases, especially carbon dioxide. This means that cutting off emissions have a very short effect. So once we stop emitting methane, it will see within 12 years the effect of our work. When we stop emissions of the carbon dioxide, the effects will be seen somewhen. It is hard to predict when. The other thing is this extremely high potential of methane in catching the solar energy. Depending on the time frames used for the calculation, the potential of methane is several times higher than that of carbon dioxide. That's why methane should be in focus, because it is one of the most effective means to hamper global warming. And this is not only my interpretation of those facts. This is the reason why methane created so many headlines of the scientific articles in recent decades. And most important scientific publishers are, if you type methane or any related record to the browser, you will see several thousands of articles that deal with the issue. This emphasizes the importance of methane. This is a little bit less discussed fact about methane, and maybe also less important for my subject, but methane and all those chemistry in the air, in the atmosphere that is related with its oxidation is highly detrimental both for plants and for the humans. As you can see, especially at low latitude where operation of sun is high, those photochemical reactions lead to many adverse effects. And even some estimates say that up to 1 million deaths are linked annually to those bad air that come from all those methane-related chemistry. This is very important picture. First of all, because it shows again this increase in methane atmospheric burden. It also shows that circa about 60% of methane that is found in atmosphere is attributed to anthropogenic sources. What I also would like to tell you is that substantial part of this methane cycle environment is biogenic. So both methane formation and methane removal from the environment is due to biological activity. And that's what I'm working with. So first of all, I will tell you a little bit about methane formation, which is called the process of methanogenesis. Methane formation occurs in strictly anoxic environments. This is because of the character of those microorganisms responsible, which are highly sensitive to oxidative conditions because of their enzyme structures that contain oxygenation, fragile to oxygenation catalytic centers. There are three main metagenic pathways: hydrogenotrophic, acetylactic, and metallotrophic. And I mentioned only three most important, I would say. But the fact is that microbial ecology is a rapidly developing area. With the development of molecular studies of not cultured and species that are found in many environmental samples, many other metabolic pathways were found. This is extremely complicated, and I will not waste your time on that. I just wanted you to show that that methanogens are in fact simple organisms using simple compounds that need to work at anaerobic conditions. But there's a little bit of nuance, because even if methanogens themselves are quite simple, I mean, by saying they are simple, I mean that they use simple compounds. The whole process of methanogenesis is not that simple, because it starts with organic matter that needs to be decomposed in the process of hydrolysis, and a chain of further reactions that lead to production of those simple compounds that may be finally utilized by the methanogenic species. So in fact, the whole process of methane formation to be carried out need activity of a huge amount of various microorganisms, including fungi, including bacteria, and finally, methanogenic archaea. Why is it so? Why methanogens are so, I would say, why they only use those simple substrate? Well, this is because they are evolutionary simple. As you can see on this graph in the upper part of the slide, methanogenesis was one of the first processes that appeared on Earth. And the first methanogens were the creatures that thrived in the primordial soup. The primordial soup was the very, very simple, I would say, soup, containing simple organic compounds. And that evolutionary dissimilarity of methanogens from other microorganisms can be seen on this tree of life, when you can see that methanogens create a separate cluster, and all the other organisms that are much more evolutionary advanced create separate cluster. So that's how their metabolic strategies are related with their evolution, in fact. Methane formation is quite widespread in agricultural environments. First of all, I think that the most widely discussed issue currently is methane emission due to fermentation, gastric fermentation of the livestock. And this is a really huge problem. Methane is also highly abundant at rice fields, and also storage and the composition of organic matter that remains on the fields or in other places also may lead to methane emissions. What's important is that among anthropogenic methane emissions, nearly 20% are related with agriculture. But agriculture is not so bad. It may also be helpful when searching for new energy sources. As it was already mentioned, methane is one of the potent energy sources, and biogas production from organic waste derived from agriculture may be one of the means to replace fossil fuels. And this actually happens to some extent. I'm not really acknowledged with the market information, but I know that in Poland, the number of biogas plants is increasing year to year. I also know that it's still not enough, but I hope it will be the branch of industry that will be developed intensively. And I know that maybe some people are not convinced by the graphs. Some don't believe. I was asked why do I believe in the measurements of the methane concentration in the atmosphere that are reconstructed from air bubbles that are trapped in Arctic ice. And some of my let's say friends who is not acknowledged with science, when I tried to explain that, he said, no, that's all not true. I don't see the problem. It all must be, it's just a problem that scientists created for themselves to have something to study. Well, recent development on the field of remote sensing and measurements carried from space, I think that would explain that person and convince him that anthropogenic methane emissions are fact and are really really intense. The first picture shows changes of methane concentration in the air column above the cow flock. So as you can see, the differences in the concentration that is above the background and the cows is quite evident. The other picture shows methane emissions related with natural gas extraction. As you can see, the pipelines, especially on the territory of Russian Federation and in here, and oil fields of Turkmenistan and Arabic states, and also US, are quite evident. The other pictures show methane emissions related with, they were not really cut to show any effect, but they reveal emissions from rice fields. Because as you can see, the geographical location is evident. So that's for all those, I would say, unbelievers. But there's also bright side of the microbiology of the soil. And this bright side are methanotrophic bacteria, or let's say methanotrophes, because not only bacteria, which I call our little knives, who fight for our security and fight against global warming. In contrast to methane formation, methane oxidation takes place at various environments. In fact, methanotrophs are found whenever stable methane concentration occurs. And since methane is abundantly present in atmosphere, in fact, you can find methanotrophs everywhere. Unlike methanogens, methanotrophic organisms are widespread around the tree of life. There are several bacteria and archaea, and they have several differences in between each other, but what they share is the ability to oxidize methane and to incorporate methane-derived carbon into their biomass. The research over methanotrophy is quite, I would say, vivid, because it started in the beginning of the 20th century with the finding of the first microbiota that are able to utilize methane, and there was used to a dogma that first, methane may be only oxidized at aerobic conditions, and second, that the microbiota that uses methane cannot use any other source of carbon. So the world for microbiologists was quite simple. There are methanogens that produce methane at anaerobic conditions and methanotrophs that consume methane at aerobic conditions. But this is no longer true because with time and as I mentioned before, with the development of new molecular technologies, it was found that methane can be also oxidized with other electron acceptors and also in an anoxic environment. So, and there are still many methanotrophic taxa that are uncovered. We only can expect that they exist. And from the thermodynamics of the reactions, we can expect what other electron acceptors can be used to oxidize methane biologically. But to date, nobody confirmed those processes. So methanotrophs are widespread in agroecosystems, and it is important to know that there are two types of methanotrophic bacteria. First, that utilize methane at atmospheric concentrations, which are very low. As you already mentioned, those concentrations are so low that they disable CO2 capture by the means of chemical or physical reactions. But methanotrophs are able to catch methane even at 2 ppm concentration. And the other group are so-called low affinity methanotrophs. This high and low affinity refers to the affinity of their main enzyme, methane monooxygenase, and the high affinity just have high affinity so it can catch the methane at very low concentrations, while low affinity needs methane to be at higher concentrations, but such concentrations occur, for instance, in soil or in anoxic waters, or somewhere on the interface of oxic and anoxic environments. And those bacteria, their activity is in fact uncovered because they utilize methane even before it reaches the atmosphere. So it's extremely hard to determine their activity because it's invisible. It's all those processes of methane formation and oxidation occur in close proximity. But without them, I guess that atmospheric concentration would be much higher. Just a few words about our research. Recently, we're focused on cooperation with some companies that try to make use of organic waste derived from agriculture. So we tried to find out whether, for instance, biochar may stimulate methane formation. That was for the purpose of enhancing biogas production. And to some extent, we were successful because biochar can mediate interspecies relations, which is important because, as you remember, methane is a highly complex biological process that requires cooperation of several species. And biochar serves as a platform that enhances this process. The other study was also related with biochar, this time put in soil, and we also found that biochar may increase the abundance of methanotrophic bacteria, which is quite good because biochar is proposed as one of the means to reduce soil depletion of organic carbon. So I think in the long term it will be used widely, and it was good to know that this addition will also enhance methane oxidation in soil. And the last slide is about my current research, which I have just started. As already mentioned, I'm trying to solve whether glyphosate, the most widely applied herbicide in the world, have an influence on methane oxidation in soil, because to my huge surprise, in spite over 40 years of study of glyphosate being applied to fields worldwide, nobody checked that. So I was lucky because that was in my field, and now we are trying to find out whether glyphosate doses put in the soil are enough to suppress methanotrophic activity. It is I think. Oh, one more. I would like to invite your taking this chance to also a conference that we are organizing in September. It will cover several issues. I think that at least some of you would be interested in, so feel invited. And finally, I would like to say that there are no conclusions from me, because in fact the whole presentation was some kind of set of conclusions. But when I previously thought about lecture about methane for the students, I decided that I will leave them not conclusion but take home messages, because everybody should know that reducing methane atmospheric concentration may be achieved by simple steps each of us could take, and this includes consumption of less meat and animal derived products, because animal production, especially wool, is highly methane emitting activity. We should also save energy whenever possible. Produce less waste, because waste decomposition on landfills is also a huge source of atmospheric methane. We should buy less clothes. That would be difficult, but it would also contribute to smaller extraction of fossil methane, because this methane is being used as a substrate for chemical synthesis. And we should also stay up to date with information and search for information in reliable sources, because there's so much disinformation in media, in social media. Politics also are trying to make their own business on people's emotions related with those issues connected with greenhouse gases. So we should stay up to date with reliable sources, and we should do science, because that's the best what we could do. And that's all. Thank you. I hope you didn't fall asleep.
I think if there's one question, we can try to answer it. If not,
I have maybe a quick one. Is there anything we can say about the use of fertilizer, just regular fertilizer in general? Does it make methane emissions more or less, or
there was a lot done in this field, and this is enormously complicated. Because this is very important, because there was a time when for example, nitrogen fertilizers were used in huge amounts, and those fertilizers include ammonia fertilizers, and there is direct relationships between methanotrophic activity and ammonia concentration. This is because the similar structure of methane and ammonia molecule. And ammonia is directly inhibiting methane assimilation by the methanotrophic bacteria. Just chemical competition, nothing else. And when there is excess of ammonia in soil or in any other environment, methane oxidation may be suppressed. However, nitrogen is also extremely necessary element for all living organisms. So when in the environment there is lacking of nitrogen, the effect of nitrogen supply in the form of ammonia will be not so negative, because this will be, on one hand, there will be competition and inhibition, but on the other hand, there will be a source of lacking nitrogen. So there was plenty done in this field, and there's still not any consensus wasn't worked out because of the extreme difference between various soils and other environments. But yes, this is very important issue.
thank you very much. I want to thank you for your presentation. Thank you. And thank you for all who survived till the end. And now we will have a lunch break if someone's hungry. And at 12:40 here, we'll start oral presentation sessions from doctorate students. So thank you.
Very good answer.